Hey guys, so good morning. We'll open the slides from the previous lecture just because there's something at the end of the lecture that we haven't talked about and are going to be sort of the basis for what we're going to see in this class. So in the last class, we were looking at the classifiers, including neural networks. And this is because this idea of classifiers and neural networks is, of course, important because you will use the classifiers to classify, for example, labels from text or sentiments and so on. Okay, so of course you need to use them as the models. Okay, but it will also be important as the models that you use before predicting something, just to transform words into vectors. Right now, we have been seeing particular ways of transforming words into vectors or documents into vectors that are not, in general, very sophisticated compared to what we're going to see from now on. We've been seeing, for example, the bag of words, which can be just binary or DF-IDF. Okay, last class we've actually seen the pointwise mutual information, which was seeing the amount of times the words co-occur, and then from there get a kind of a score of those words appearing together. But we are going to see now a way which is probably might be the first thing that actually revolutionized the area of NLP, which is this idea of word vectors and word-to-vec that come from this model called the skip-gram, which is the one that we're going to see. I know you talked about this in the labs because, of course, the lab was before this, and the idea was to show you how to use this in Python. But now I'll try to unpack, and we have slides from the labs, I'll try to unpack again how this works with a few examples. Okay, so again, the idea is that one of the problems that we have with bag of words and singular representations is that we have very sparse vectors. Okay? Vectors become very big, generally the size of the vocabulary. That's a problem. Another problem is that generally we are not able to capture semantics, which are the relationships between words, like gender or plural, text, stuff like this. With the skip-gram, the model that we're going to see next, the idea is that we are going to be able to create much smaller vectors and vectors that are actually able to understand these relationships between words. So, how does this model work? Okay, so the idea is to train a classifier, which does not necessarily need to be a neural network, but it at least it will look like one, and might be a neural network, but it does not need to be exactly a neural network. And we are going to say to train a neural network to predict given a word if another word is or is not in the context. Is it the next word or is it the previous word? Okay, or two next words, or after, or two previous words. Okay, which means that you'll see an example, but pretty much we're going to see if even a word, another word is in the neighborhood of that word. That's the idea that we are going to use. Pretty much what this assumes is that similar words or words that have some sort of relationship tend to appear together. Okay. We've seen this, it's the same intuition behind the pointwise mutual information, which is that words that appear together or a lot of times appear as the context of another word tend to be related. So information appears a lot of times with data. Okay, probably information does not appear a lot of times with the word share, for example. Okay, so this means that these words have some sort of relationship, and so their representations should be similar in certain aspects at least. Okay, so for example, we'll see later representation of king should be similar to the representation of queen, some aspect, right? Because they kind of mean the same thing, and they tend to appear together with the same words. Okay, so maybe king appears a lot of times with the word crown. Probably queen also appears a lot of times with the word crown. So the idea is that we're going to create this lexical campus of words that appear and together with other words, and that's going to be the basis for the creation of this model. Okay, so but this is actually a dummy training process. So we're creating this model to predict next word or previous word or similar, but we are not actually going to use this model. Okay, we don't need the model. We don't need to predict the next words. What we want from this model is to extract the weights. The weight matrix. You can think of it as a neural network weight matrix. Either the final one or the first one that multiplies with the hidden units. So that's going to be the idea. We extract those weights will be the representation for each of the words that we have. So pretty much the model will be something like this in terms of a very simple view. You get a word, you pass it through this word to vec, and you get an output as a dense vector. Okay. And of course, we will define the size of the vector before. Okay. Generally, bigger vectors will give you more information, but they also might be more costly. Okay. So how can we get? Let's see step by step how we can input a corpus and extract word representations, vectorial representations. Okay. So let's say that we have this, it's a bigger corpus, a bigger text, but we have, let's focus on this particular sentence inside a larger corpus. We are going to start by creating a table where we're going to enumerate each combination of contexts and words. Okay. What this means is that, okay, so we are going to select a word. Let's say we select master. This is our word. Okay, and then we need to say, okay, what words are contexts of master? And this could be the word before, the word after, 2 words before, 2 words after. So then you define what's the window that you want to consider. In this case, let's consider just one after and one before. So you define the words master, the context, and then you just need to mark it as a 1. So this happened in our corpus. Terrible comes after master. So that's pretty simple. And you will do this for the word after as well. So master, but is a context of master, mark it as 1 because it happened in the corpus. And you do this pretty much for each sliding window of words. So then we have but as the center word, master, and appear next to but. And then you, of course, will extend this and just have a giant combination of the word and its context. Okay. So we are just here creating, what we're doing is creating the training data. Because remember, the objective of the model is to give a word and a context to predict whether or not this word comes in the context. The context comes after the word. Okay, so now we have a lot of positive examples. So the model cannot be trained on with positive examples, right? Because then it would always output 1, always output that. Okay, so this word is a context for the central word. So what we have to do is to have negative samples. Okay. So our negative samples will be words that are part of our corpus, but never appear together. So ring never appeared in our corpus after or before master. So this will be a 0. It's randomly done, okay, the idea here. And now we get a corpus that has both representation for ones, for positive classes, but also for negative classes. Master variable, target 1, master ring, which never happened, target 0, and so on. Now we get relative representation for each of the possible targets. Okay. And now the task, as I was saying before, will be for the model to given these words and given a context to predict whether that context comes with that word. Okay. So we don't know. The model will not see the targets. Of course, we know the targets. This is like training a model. Just need to train them to predict whether or not for each iteration, okay, so now master enters the model, and the model needs to predict whether the next word is terrible. Target is 1 here, so the model should be able to predict 1. Okay. In the first iteration, might not predict 1, of course, but as you train the model, like you train any neural network, you'll be able to make it a little bit better. Okay, so you go pretty much through each of the words. Okay, second one, third one, and you go through all of them. But if we can zoom in a little bit, for example, in one of the training steps. So let's say master goes through model to predict this word. How would the training go? So the inputs for this model, I'm just calling it model for now, but we'll unpack it a little bit. But the input will always be something like this, just like a column which has zeros and a 1 in the words that we are considering. So it will just be a giant column with all the words. Each word will be a row. And if we are trying to predict, for example, at this point, we're trying to predict master. So master will have 1. If we're trying to predict for terrible will have 1, so on and so forth. So it's always something like this. So the actual inputs, if we transpose it, because how it enters the model, will be something like this. A lot of zeros, just a 1 in the position of the word that we are talking about. Now, this is sort of the first step. And then the next step will be something like this, kind of like in a neural network. We have our inputs, and we're going to multiply it with a set of weights. Okay. The input is going to be 1, so the result will always be the weights value, the weights value will result in even states. Okay. It's like in the neural network, we generate these weights here. Okay. Pretty simple, just like a matrix multiplication. It doesn't even actually need to be a neural network. Now, the thing is, at this point, when you define the number of weights that you're going to use here, we're actually defining what's going to be the final size of our vector, of the vector that will represent words. So when defining the amount of hidden units, let's say, you're going to have to, if you want to have a vector representation of 100, a vector size 100, you need to define 100 hidden units or weights. And if you want to have 50, you need to have 50 hidden units, and so on and so forth. So at this point, we'll define what's going to be the final size of your vector. Right. In this case, we're going to end up with a vector of size 3 because we are considering 3 hidden units. So the idea is that you're going to multiply with this matrix, which generates hidden units, which will be the size of the weights. Then multiply with another matrix later on, so that you can just put it into a sigmoid function, which is going to give you an output. Okay. So this is really just, or either a simple neural network, or just you might not even consider necessarily a neural network, just a classifier, which is going to give you the probability of master coming after terrible. Okay, so the sigmoid allows you to output 0 or 1 sigmoid function. And you get this output, which is going to be, for example, 0.65. You pass through some loss function. In this case, very simplified. You calculate an error, and you can backpropagate it. Okay. So backpropagate it using gradient descent, for example, as we saw in the previous class. What happens is that for each of the examples that you're going to pass through the model, master, then money, but, and so on, it's going to have a prediction, turn it back, upgrade to weights, and you will end up with a final matrix of weights. So you don't really care about the previous model. What you care is about the matrix of weights that you calculated for each of the words. And this matrix of weights will be the embeddings, the word vector for the words that you have in your model. Okay, so for master, it will be the weights connected with master that were trained. And sometimes it can be just this matrix of weights, or it can be an average between these two, this and this one, or something like that. But pretty much for master, you'll have this set of weights, which was trained to predict the next word. You retrieve these weights. For other words, for example, your money, you retrieve the weights that correspond to money. And so the values of the weights will have to be a vector, which will be the vector or representation for the word money, for the word master, and all the other words. And they are three, again, I was saying that the embedding representations, the size of these representations is defined when you define the hidden units because of this. So it will always be the size of the amount of weights that you will use in the first layer of the classifier. Okay, so based on this and what you've had in the lab, questions? Okay, so what's the output of this in terms of something useful? Now, once you calculate these vectors, turns out you are able to, when plotting the vectors, of course, you need to reduce dimensionality to plot them into 2D space. But it turns out they are able to capture semantic information. And of course, the bigger your corpus and the larger the embeddings, the better. But just even small embeddings are able to capture some things. And what this means when I say capture is even we're talking about distance between vectors. So, for example, the difference between aunt and uncle will be very similar or equivalent to sister and brother. Okay, the way you can plot them spatially. The same thing between we've seen queen and king. They will have some distance which will be similar to something like madam and sir. Even the different inflections of words, slow, slower, slowest, will have some sort of movement that will be similar across multiple words. Okay, so at this point, what happens is that some of the preprocessing that the preprocessing step that you were applying in your pipeline, especially during the labs, okay, lemmatizing and so on, they stop making that much sense because now you are able to represent these words and they have some meaning in relationship to other similar words. Okay, so preprocessing after this becomes a little bit more limited or with less effect when compared to what it was for a bag of words. Okay, here are other examples of extracting word vectors with word2vec or scheme when using corpus from some time ago, then using corpus from like 15 years ago, and then corpus with 20 years, and see the difference of how words move and how they relate to other words throughout the years. So this is interesting because you can study like the evolution of words and the evolution of their meaning in relationship to other words. Okay, this thing here, you can check it out. I'm just going to show you super quickly. This is just word vectors computed in a 3D space after PCA, principal component analysis, and it allows you to check, for example, a word and check what are the similar words to that one. Okay, so what are the ones that are closer to it, and check how they plot in space. So this is kind of the output of a word to vec, of course, not in 3 dimensions. It could be, but generally not. Okay, so what happens is that once you have this, you're not necessarily going to train your own word to vec, okay? Because for this to work very well, you need a giant corpus. Okay, so some of these are trained in Wikipedia, in Google News and stuff like that. So what you can do in the project with Word2Vec is to call some pre-trained model. That's I think what you've done in the labs, and you're going to use that. Okay, you're going to just pass all your words to the Word2Vec, which returns the outputs. It's going to be a vector representation, and then you use that as input for a model, which is going to be another challenge that we're going to look now, how to use it as an input. So, of course, then you will be able to extract very powerful representations, and others that may be smaller, not that good. What generally can be done is, so you use pre-trained vectors, that's how they're called, pre-trained, because they're already considered given another corpus. And what you can do is fine-tune them with your own data. So some of them allow you, not all, but some of them allow you to, okay, we already have word vectors. We're not going to randomly initialize our weights to train the model, but we can train just a little bit more the model with our own corpus to make sure that it's allows us to be a little bit domain specific. Sometimes your data is might be domain specific, which means that it's not so generalizable to other things. And it's good to fine-tune the model needs to learn a little bit about that domain without destroying the rest of the training that was done by someone else. So that's an advice regarding what you could do in your project. I think that in general, the language that is used in the Airbnb reviews and so on is not that domain specific, so you will not really require your model to be fine-tuned. Maybe you can just use the pre-existing ones. Questions? Okay, then I have here some. So now, besides having those types of representations with tag of words, the FIDF and so on, now you also have word embeddings as one of the ways you can feature engineer your inputs to enter models like logistic regression, neural network, decision trees, and so on. But now here comes the interesting question, which is, how can we use word embeddings to enter neural network, for example? Because what happens now is that our documents, our sentences will not just be a vector, but they will be a sequence of vectors. So there will be nested vectors in a sentence.
Can I ask a question?
So what's going to end up happening is that once we turn every word into an embedding, into a vector, every sentence that we have, every document will become a sequence of vectors. And so we'll have sequential inputs, which is a little bit different from what we've seen before. So once turning words into vectors, instead of turning sentences into vectors, what will happen will be the following. So let's get this sentence, which is pretty simple. No pain, no gain. For each word, we have an embedding. Let's say size 3. It could be size 10, size 100, size 1000, but make it simple, let's make it size 3. So we use Word2Vec to extract embeddings for each word. Now I know as this embedding, a vector, another vector for pain, another vector for gain. So when representing the entire sentence as a set of vectors or as a vector as an input, we'll have something like this. So no, which appears 2 times, represented as this vector. That this vector here. Right. Then also for pain, another vector, and also for gain, there another vector. So we'll end up with this sentence becoming a sequence of vectors. So how can we use this? Because of course there are sentences that have 3 words, there are sentences that have 100 words, and, right? So how can we use this to enter a model like a neural network? Because a neural network, if you remember, it's kind of fixed input, right? You have features don't change based on the inputs. Okay, so in a bag of words, just to recall, we had something like this, where you have for each word a binary value, and then that's used, that vector is used to enter the network there. Okay, 110 for the first sentence, review 1, a great movie, 11, bad doesn't enter the first review, so it gets a 0, and the value, the amount of features that are going to be considered for each sentence is also going to be the same because it's the size of the vocabulary. Now, how can we use, instead of 0s and 1s, now we have something like this. How can we now use this and insert it into a model? Because now grade is not just 1, movie is not just 1, it's actually a vector. So you're going to see that this will not be so straightforward, the way in which, and there are different alternatives, the way you want to input these representations into just one feature. One of the options would be to average the vectors to get a final sentence vector, a vector for the sentence. Okay, you take the vectors of all the words that you have, you average it, and you get a single vector that represents the sentence. Now, of course, that will result in losing some information, because after all, you are reducing the information that you have across the multiple words. They have their own meaning, and you're reducing to something unique that might not capture everything. But then you can use it. So the input will be the size of the embedding that you initially defined initially. So you can actually input it now, and it might give you a good result actually. So this might be a good option in this sense. And the biggest difference between these 2 approaches is that the word embeddings at least give you dense vectors, which are small vectors, compared to the word bag of words, which will give you a very sparse vector. It will be the size of the vocabulary, it will be the size that you define for the word vector a priori. So it's a good option to do this, of course. But what if you don't want to average or sum or concatenate the values to get a single vector? What if you want to consider the entire sequence of words with their own representations? Because after all, you did create the representations, now you're throwing them away more or less. So what if you want to keep those? Just before I continue, any doubts regarding this? Okay. So what we're going to do is to use other networks that allow us to actually deal with sequential information that are done for that. They are created to manage input that comes sequentially. Okay. And those will be recurrent neural networks and long short-term memory neural networks, which are just a variation of the recurrent neural networks. And these are models that, of course, they are not just for text mining, because text mining is just one of the tasks that generally has to do with having sequences of inputs, because a sentence is a sequence of words. Forecasting is also something that in which people tend to use recurrent neural networks or LSTM, because it's kind of the same thing. You have a time series, you have a set of events, you want to predict the next event, so you need to know the sequence of how the sequence of the events took place. So these are going to be what we're going to be talking now, and they also allow us to do more complex modeling and more complex predictions, okay, which includes sequence labeling. So, for example, saying what each word is about, like identifying geographies, identifying entities, identifying numbers, dates, and so on. So it's possible to do it with these type of models. It's hard or impossible to do it with simple neural networks or other simpler models. Sequence classification, which is a thing that we are actually trying to do, getting a sequence, classifying what's the sentiment or what's anything, the label of that specific sentence. Language modeling, which we saw we could do just with probabilities, but it's also possible to do it here. So to understand what's going to be the next word, for example, or how likely is a sentence to appear, and translation. Okay, so you get a sentence, you encode it, and then you can decode with another RNN. So you use actually two, and you get an output of a sentence. Okay, so we're not going to look at the ones that are not with the red circle. That's why I have the red circle there, because those have their own types of approaches. We're going to focus on sequence classification because this is the same thing that you're doing in your project, and it's maybe the simplest one, which will serve as a baseline for maybe later you understanding different types of tasks. Okay, so start with recurrent neural networks. This is it's very similar to neural networks. The only difference is that you're going to, in general, keep the information from previous steps. Okay, so the value of a prediction will always be based on previous prediction. I can say that. Okay, so you'll calculate an hidden units at the input point of view. Will not just be the weights times the inputs, which is generally what happens in the neural network. Weights times in gives you the value of the hidden unit. It's the weights times the input plus the weights times the output of the previous step on the network. Okay, again, we'll unpack this with more detail, just to give you an overview, and the output will be then a function passed through the result of this multiplied by other matrix of weights. So it's always matrix of weights on and off. So this is kind of how you would look at it. I think this pretty much tells you the main idea. So we have three words. Word one will enter. It will produce a hidden state, which is moved to the next word that enters, and the next word's prediction will be based on the current word plus the previous word. And then you do that along the sentence. So all the words that you have in a sentence will have their own representations. They will enter the network. You try to make a prediction, or at least to generate a hidden state with that specific word, and that hidden state will move to the next words, so that it will give you not only the information at the end, but also try to give you the information of all the words that you have across the network. So again, some more examples. This is how you could transform it kind of in an algorithm. Okay, so you're always iterating, calculating new hidden states, and then using it to produce the outputs. Another way you can view it is each word as a representation at, let's say the sentence is the length of all these inputs. Each word will enter and inform the next word that will enter the network. So again, here in a more dynamic representation, what happens is the input gets in, it's concatenated or multiplied with a previous hidden unit, passes a 10 function, which just puts the values between -1 and 1 so that they don't explode, they are not too big. And then it gives you the output for the next cell or the final output if it's the last word.
So it's like a really long sentence, all of the words get concatenated and then only together go into the activation function.
So a word gets concatenated with the previous one.
Just one.
Just one, yeah, for you, okay? We'll see the different approach.
It's not like a really long chain. Always.
Yeah, always two, yeah. In this recurrent neural network, yes, LSTM, it's kind of like what you're saying. So here it's always the previous one that is connected with the current one, passes through this function to squash the results, goes to the next unit, to the next word. Okay, so here another way of looking at stuff. Let's say we have still that review from the previous example, where we didn't know how to input it into a network. Create movie has those embedding representations, and it will enter a network just like the first word that gets in. It's like a normal network. You have a representation multiplied by weights, generates an hidden state. Okay, and then of course you can have multiple hidden states. Then you can extrapolate this, but very simple one. You get an hidden state generated, this H. Now, you're not going to make the prediction immediately at the grade level, because of course, this is the first word and you still have movie. So there's more information to consider. Then you press movie, which will get its own inputs, but will also get the hidden unit of the previous state. And then of course, those are multiplied, squashed to a function and passed again to another matrix of weights here, V in this case, and you get an output. So your final output is always informed by the chain of events that happened before. Okay, so here another example with numbers. Grade goes first, then generates hidden state, passes it to movie and generate the probability for positive in this case. Questions? So, do you see any possible problem with this type of network? Okay, so we have a couple of main problems here. They kind of related actually, but one of the problems is that we're always going to consider more information, or the weight of the last word that enters the network will always be greater in terms of the impact it gets in the prediction compared to the weight of a first word, especially if we are considering a long sentence, and that's kind of what you're saying. So because we don't have the first word being considered for all entrances, we just have an hidden state being calculated at each point. The hidden state will not be considering the first words, at least when you reach the last word. That's called a long dependency problem. So here's an example. So imagine that you wanted to predict the word that comes after fluent in this sentence. You're using a recurrent neural network and you outputted the probability of being French, this word. So you know that it's going to be a language because I speak fluent. Fluent generally comes with a language in the language after. It might not be French. For you to know it's French, you need to go way back on the sentence and get the word France, which should have an impact on French. Okay, so since we are not really focusing on France when we're creating this recurrent neural network, nor in any word in the beginning, will not be able to inform that well the last hidden units using the first input. Okay, so that's kind of the problem of long dependencies. Now we're going to see ways of solving this using, for example, LSTM. but we're also going to see the attention mechanism, which is another of those revolutions that happened in NLP in the recent past, which makes this even more efficient. Not today, but in the next slide. Another problem is the vanishing gradients, which is this idea that the first words will not have a great impact in updating the weights of the network, okay? Just because, like the example before, in this specific case, for the sentence to be predicted, because the last word here, French, also predict that the next word will be French. France should be the one that maybe has the highest impact on the updating of the weights, right? The one that moves more the weights towards being French. Next word. Now, of course, with the current model that we have, we don't really have nothing that is able to point out that some words should have more impact on the weights, or that when we are using gradient descent to update the weights, that specific weights should also be better updated. So another problem is this idea of the vanishing gradients. As you go through multiple steps, the first step stops being able to be updated that well. Okay, so one of the solutions for this, and this, for example, doesn't make much sense in forecasting, let's say, but makes a lot of sense for text, is to make the model bidirectional. So you'll have one recurrent neural network passing from the left to the right, and you have another one, actually it's just one, but you can think of it as two, that will pass from the right to the left. Okay. So that you move, the last word that you consider will be first, and on the other side, the last word is actually the last word. So here, the word that gives the output on this recurrent network will be movie, but on this one that moves to that side will be great. This is a way of trying to give importance to words that are in the beginning of the sentence as well, and then you concatenate both hidden states. You pass it through a classifier, which will give you an output. Okay. So this doing it both ways, just make sure that you look the sentence from one side to the other and from the other side to the end. Okay, left to right, and then right to left. Concatenate the hidden states from both options, and then get an output from there. Just stacking to recurrent neural networks in different directions. So of course, again, this is something that if you're going to implement a solution like this, you're going to do it eventually. You just need to call like a bidirectional layer, and this is easy to do. It's not necessarily something that requires a lot of engineering to stack code. Now, another solution for the problems we've seen, which include vanishing gradients and long dependencies, is this idea of LSTM, long short-term memory neural network. So the LSTM will be very similar to a neural network, except that it will not consider just the hidden state of the previous words. Okay, so we'll have two main ideas here, two subproblems being encoded. One is which information should we remove from the previous steps that is not really important from the current step, and which information should be added to the current step. So that's the two things that the LSTM will always be trying to solve: what should be added and what should be removed. With the recurrent neural network, you're just going to say we are adding always the previous step. You're not really deciding which part or not should be removed or added. So those will be two things, and it's going to do this via two different things. One will be a cell state, which is something that will run across all the units in the neural network, and also true gates, which are pretty much just activation functions that will decide what information to keep or to leave from the previous steps. Okay, so the idea of RNN and LSTM is pretty much similar. Always have an input, which is going to generate a hidden state, which is going to be passed to the next, and so on. It just differs on how the calculations that you do inside the LSTM itself. Okay, so let's focus a little bit on this because it's not that complex either. Okay, sometimes it will be hard to get it at first, but overall, if you look at this with more detail later, you'll see that it might not be that difficult. Okay, so the notations that are going to be used will be something like this: red sigmoid, tan, and then we have the pointwise multiplication, addition, and concatenation. Okay, so what the sigmoid does, just to remind you, is to put the values between, any values will be between 0 and 1. This will be very useful because values that will be close to 0 or 0 will, when multiplied with other values, will give a 0. And the tan will make the values between -1 and 1, which will be good for us to make sure that our values don't get too big. So, as I was saying, two things that will be considered here that are mostly important are the self state or context layer, which is the thing that runs across the network, and the gates of the network that define what's going to be forgotten or what's going to still be used from the previous states. So that's the self states. The idea is that instead of always considering the previous hidden units and changing the values for each timestamp, here we are going to do timestamp. We can say that timestamp it's a word, like timestamp 1 would be the current words, timestamp +1 the next word, and so on. So we'll always have a self state from the previous word that's going to run across the network, and it's going to be updated in each word and result in another self state. Now the way it's updated, it's optimized to make sure that we don't delete information from the beginning of the sentence if that information is important. So while in the recurrent network we just consider the hidden state from the previous sentence, from the previous word, you can think of the self state as a general hidden state of the entire network, either from the first word or the second or the third, and so on. So it will try to keep the information of all the sentence. To define what's going to be carried on these self states, you have neural units, which are the gates, which are these things that we've seen here. These gates here, that we call it gates just because they work as gates of what passes and what is kept from moving on. We'll have three types of gates. Forget gates, which in the beginning will decide what should be forgotten from the self state, what no longer is necessary from the self state. An input gate, which is going to define what's going to enter the self state, and an output gate to define what's going to leave the self state at that timestamp, at that word. So the forget gate, it's actually going to use the previous hidden state because we're still defining a previous hidden state, and it's going to use the current input, pass it to a sigmoid function, which is going to select define values between 0 and 1, and this is multiplied later with the self state. Okay, so here what's going to happen will be something like this. So this is exactly like in a recurrent neural network, this first step. Okay, we concatenate the hidden state of the previous with the inputs, we pass it through a tan, and it moves on to the self state. Actually, to sigmoid, sorry. So this is the forget gate. We'll see what we'll do with this with the output of this activation. But pretty much remember that it will make it between 0 and 1. Again, it means that values of this embedding that have 0 will be kind of discarded. Now the input gate, it's a little bit more complex because it has two steps. Again, we're going to use the last hidden unit and the current input. We're going to pass it through a tan layer, a tan activation function, but also through a sigmoid. Now things, of course, why this is done, it's a matter of understanding what's going to be the output of passing a sigmoid and multiplying it with a result of a ton, which will result in some zeros. And of course, this requires some error and trial to generate this idea of what should be the correct gate to keep here. And so the people that developed this idea, of course, were analyzing what would be the different outputs of considering different types of layers. Okay. Okay, so what happens here, it's similar at a certain point with the previous one. Okay, so what we're doing here is pretty much saying, here we're going to define what we want to forget, and here define what, and here just reducing the results to be between -1 and 1, because this is the ton. And then we multiply it so that we are defining pretty much what from the current inputs we want to keep or forget. Okay, so we multiply sigmoid result with a ton result. This is an input gate because it's going to actually be summed with the cell state. Okay, we're going to add this information to the cell state. Okay, so when you, after calculating the forget gate and the input gate, what's going to happen is that you're going to update the cell state. We saw before is this thing that passes across the network. So how is it updated? By the forget gate, it's multiplied with zeros and ones pretty much to see what's going to be kept. And then we add the information from the input gate, which is going to define what's going to be added, what's new is going to be brought into the cell state. And then we have a new cell state for this current iteration. Now this cell state is going to be moved for the next word, if that's the case, or it's also going to be considered for the output of this current one. Okay, so the output of this current one will be the multiplication of the input, which is hidden state and input actually, and then the current cell state multiplied with that input, and it gives you the hidden state that's going to move on to the next part of the network to multiply with the input. If this is the last word, this hidden state will be used then to classify what the label of the sentence or whatever you're trying to classify or to predict. Okay, so we can look at this in another way, maybe a little bit more complex. We have a cell state, we have the previous hidden state, and we have the inputs, and these all things are going to be multiplied in order to reach both the cell state and the new hidden state at this time step. Okay, so here, just looking at it with many different words. So each word would be something like this, a vector like that. So it's then we pass it throughout the network. So kind of like in a recurrent neural network, but of course then we have some more complexity inside the different gates and the different hidden units. So it's important that you understand this for two reasons. First of all, because it will allow you to better understand how you can, for example, change the hyperparameters of the network and see how this can affect different things. But also because if you want, for some reason, which might not be the case, since this is advanced analytics, not necessarily engineering, but you try to build your own network for some reason, you need to know how things work for you to implement them. Now, in most cases, you'll be able to use TensorFlow to implement this very easily. Just need to call TensorFlow to call the LSTM or the recurrent neural network and apply it, and you'll be able to do so. It's always also important to understand this because there are some mechanisms of when you call this in TensorFlow that will give you errors in the beginning because you won't know. So what could be the size of my input? You need to define that. You need to define some of the units here, what's the size of the outputs, and there's a few things that you need to configure that require you to know at least at the high level how things work. Okay, so one of the things that this model, the implementation requires you to do is to do padding. So padding pretty much is to decrease or increase the size of the sentence. Because remember, the input of a neural network needs to be always the same size. Okay? It's 10, if a sentence is size 10 and another sentence is size 20, so 20 words versus 10 words, they still need to have they'll still be multiplied by the same amount of weights, and they have the same amount of pictures to enter a model. Okay, so what I mean by this is like here. Okay, so the model will require you to define that the input is size 2, for example, if you have 2 words, or it's size 3 or 4 or 5, but it's going to be the same for every sentence that you have. So if when defining a recurrent neural network or LSTM, you need to define first what's going to be the size of your input. Okay. Generally, imagine this is a sentence that we have in our corpus, but there's other sentences on average that are size 20. So or the maximum sentence is size 100. So your input should be size 100. What that will require you to do is for sentences that are smaller, you need to pad. Pad means adding like dummy tokens to the sentence so that it becomes length 100 as well. Now you can also, so beforehand, when using LSTMs, you'll see this on a practical class, you'll have to do this padding, adding dummy tokens, adding dummy words. And those dummy words, you can give them representations of just zeros. For example, the embeddings of those dummy words will be just vectors of zeros. And then you can implement a layer of masking. I'm not sure if you're going to see this on the practical class, but then you can search for it, masking, which allows you to just hide, like from the network, these zero padding values. So while using padding, you still can use masking, and it's like if you didn't have those padding tokens, at least the network is not trained with those padding tokens when you use masking. In any case, even without using masking, generally the network is able to perceive that those zeros are not important for the prediction, so it will not really use them for updating the waves. In any case, remember, padding you'll see on the practical class will be something that will define the size of the inputs, and masking will allow you to overcome some of the shortcomings that padding may have. Okay. So from the next lecture and on, you'll be able to not only now use word embeddings, which in some cases might have multilingual information. If they were trained with a lot of language, they may be able to capture some level of multilinguality, which allows you to consider the multiple sentences that you have in different words, the reviews. But you can also use LSTM, which allows you to, it's generally more powerful for sure than just using normal neural networks, because it allows you to process the sequences that you can extract from word to value. Those are the main ideas. Word embeddings are now sequences of words, much more strong. They are able to get semantic relationships between words. You can input those word embeddings into sequential neural networks like the LSTM. We should consider the entire sentence to make a prediction of a class of the text. Any questions? Okay, so as we're going through now the next classes, we're going to start delving into things that are a little bit more complex, maybe. Like this idea of the LSTM might be a little bit scary when you look at these things moving on at first, but as you look at it closely, you'll see it's not that complex. And now we're going to start moving in the direction of state of the art. Okay, so LSTM, like maybe 10 years ago, was used a lot along with other models, but today we have different things. We're going to start slowly entering the realm of the transformer, which is going to be maybe the basis for the large language models of today. And next class, we're going to start entering on that part because it's right after what we learned today of the LSTM. Okay. If you don't have any questions, see you next week.